So we are going to see the simulation of the proposed protocol in a Scyther tool. So Scyther tool looks like this. This is the platform where we need to write the protocol, and we'll verify the protocol using the verify protocol menu. So before verifying, let us understand what is the protocol, how to let's understand the protocol and its simulation construct. Then we'll verify the protocol. Before starting the protocol, we need some user-defined variable. So user-defined variables are created like with the help of user type is a keyword in Scyther. So it is the keyword used to define the user type variable. So user type transaction is a user type variable created. Transaction can be assumed as a data structure for transaction. Similarly, a response is a result response data structure can be of user type variable. Hash function is a keyword, and edge is a hash function used to create the message digest. Similarly, also we have XOR function, which is also a user type variable, can be used as the XOR variable, an XOR operation. So protocol starts here. The protocol starts with the keyword protocol, and the protocol name is given as blockchain blockchain authentication. We have two parties involved in the protocols, and parties are denoted as NI or the IoT node, and the PX is the peer. And the protocol starts with the opening curly braces and ends with a closing curly braces. And within that scope, we need to define the role. NI is the IoT node and role PX is the peer. Role is the keyword to define the role or the structure or the functionality of the parties involved in the protocol. So NI is the IoT node. As per the protocol, it will generate the random nodes. So to denote the random nodes, which is been freshly generated by the IoT node, fresh keyword is used to denote that R1 is the random nodes created recently. It is recently created the true random node, and it is of type N1s. Then it will send the random nodes by using the send1 index. Send1 index is to denote the send message item, and corresponding receive message receive index is to be put to denote the receiving a message. So let's look at the send1, which is being sent by the IoT node. This is the construct of the Scyther. The sender and receiver has to be denoted in the message construct. So NI is a sender, PX is a receiver. It is a generic construct of the message in the send message packet. As per the protocol, the IoT node will create a packet with this construct. So what the construct says, it has the sender address, that's NI. Along with that, it will have a random nodes R1 digitally signed with the secret key of NI. This is how denote the encryption is denoted with the curly braces, and SK is the secret key, is the keyword used by the Scyther tool to denote the secret key of NI. And the whole packet, the sender address NI and the digitally signed random nodes will be encrypted using the public key of the peer. So PK is for public key. This is how we use for encryption, the encryption construct is denoted like this. So opening curly braces, closing curly braces. This will encompass the message that we want to encrypt, and PAK is a keyword used to denote the public key of PX and to be sent to the PX. PX will receive the message with the same construct because message has to be of same structure. So once it will receive, to receive the messages, the if you want to extract the value of R1, then R1 is the random node sent by the role NI. So if you want to receive the random nodes R1, then we have to create a variable. This is variable, where type variable, and where is used is a keyword to denote the variable R1, and the type is nodes. Now look at this. It has received the message and claimed that peer is running live with non-injectivity property with random nodes R1 and R2. So we need to check whether this claim establishes or not. But before that, we need to send the random nodes which has been created by the PS as well. So as per the protocol, after receiving the random nodes R1, it will generate the random nodes R2, and fresh is the keyword used to create the random nodes freshly, although it is initially the first instance is created by the PX. The fresh keyword denotes the fresh instance created by the PX, and it is of nodes type. Nodes is the variable type, and will send it to the IoT node. So sent message is indexed as 2. So as per the structure of the Scyther, PX is the sender, NI is the receiver. It's a send packet structure. It has to write this. The message is PX, the sender address. Along with that, it will generate a shared symmetric key using the XOR functionality, and the random nodes R1 received from the IoT node and R2 generated from this peer PX. So we saw that R1 is received from the peer, and R1 is received from the IoT node, and R2 is created by the peer, and both R1 and R2 are operated over XOR functionality to generate a new shared symmetric key. Along with that, it will also send back the received random nodes R1. And while sending these messages, this will encrypt using the public key of the IoT node, the sender IoT node NI. So once it will send the send message index 2, we send to the IoT node NI. So we'll go to the receive to message. So role NI, look at this receive to. Receive to will receive the packet, and it is being sent by PX, and NI is the receiver. Structure is same. PX is the sender address, XOR is the functionality given, XOR function, which is operated over R1 and R2 random nodes, and R1 is the random nodes sent by the IoT node NI, and it is encrypted with the help of public key of NI. Once it reaches with receive to index to IoT node, it is assumed that it is decrypted because public key of NI is used to encrypt the message, and NI holds the secret key of its paired secret key. Hence, the message is decrypted, and it also claims that NI is running fine, running alive, and with the variable R1 and R2. So we'll see the non-injective property, which ensures that its contemporary or its peer node PX is running alive. So once it is done, the IoT node will generate a fresh variable transaction S, TRANSX of transaction type. Transaction is a user type variable which we have already created before using the protocol. So this is a user type variable is created, and it is the first instance. That is why we are writing fresh to denote that transaction X is created by NI, not other than any other. So the fresh denotes that the variable is created by the sender only, and it is not created by any other parties. Then using the next send message with the index 3, it will send the packet. NI is the sender, PX is the receiver. It will send its address IoT node NI, and it will encrypt the transaction with the help of secret key of IoT node NI, and it also send back the random nodes received. R2 is random nodes created by peer, and it is sent to IoT node. IoT node has received, and it is sending back this IoT node, random nodes R2 to the peer. And while doing that, it will use the shared symmetric key or R2 as a shared symmetric key between IoT node NI and PX. It also send the message digest using the hash function h of the transaction X. So when it is sent with the index 3, we'll go to the other side and see how it has been received. So to receive the transaction X, we need to create the variable. So variable is created. Variable is a user type variable. It's a second instance variable to receive the message. So when we are sending any fresh instance, we denote by the keyword fresh, and once we receive the value, we need to use the variable var as a keyword to create the variable. Now receive 3 denotes the corresponding message of send 3. So NI is the sender, PX is the receiver. The message construct is like this. NI is the address of the sender. Transaction is being encrypted using the secret key of NI. And R2 is the random nodes. R2 is again used to encrypt the whole message. Because R2 is sent by the peer node PX, so R2 is known to PX. So this message can be decrypted using this R2 symmetric key. And along with that, it can also extract the transaction X. Because this public key of NI is available to every other party in the framework. So transaction X is encrypted using secret key of NI. So by using the corresponding public key, the peer can decrypt the message. Along with that, it can also check the integrity of the transaction using the message digest H hash function of transaction X. Further, it will create another result which is freshly generated by the peer node executing the transaction of response type. Response type is a user type construct which you have already created. So next, the peer node will send with the index 4. So it is the message 4. PS is the sender and I the receiver. It will send its address PX along with the digital assigned response. So digital assigned is a secret key of PX. Peer is used to sign the response, and R1 is the random nodes to signify that R1 is sending. R1 is the random nodes generated from IoT node, and it uses R2 as a shared symmetric key for encrypting the whole message. The shared symmetric encryption is denoted like this. R2 is shared between NI and PX. The result is written R2 moon bracket NI comma PX to denote the symmetric key encryption, and the message is enclosed with the curly braces. Along with that, we are also having the message integrity. content that is a hash function of response x. So we'll see the corresponding receive for message of the other side. Receive for is a message will received by the IoT node. Px is the sender and I is the receiver. Px is the sender address. Response x detail assigned by Px are on the random nodes. So here the IoT node has the random nodes R2, so it can decrypt the message. It has also the public key of peer, so it can decrypt the response also, and it will check the message integrity of the response X. So by this we establishes the two-way communication exchange of random nodes between node Ni and peer Px. Now we'll see the various claims that need to be established while running this protocol. So what is our claim? Non-injective secret of R1. R1 variable and R2 variable need to be secret, so no other party can influence or know the random nodes R1 and R2 in between this in communication. So these communications are happening over an unsecure channel, so anyone who is pressing the message will not be able to know the value of R1 and R2, so hence it is a secret or the confidentiality property. And the IoT node need to be alive throughout the session, so this is the aliveness property is to be tested. Weak agreement, the message agreement has to be properly tested while sending the message. The intruder should not be able to change any message, should not be able to modify, alter the message in between the communication. So that is need to be properly checked using the weak agree property of the protocol. So weak agree is used to check from from NI side, so IoT side. Then commit is the protocol sequence needs to be properly synchronized for peer Px, and then those R1 and R2 need to be properly addressed. It will also check non-injective agreement. That means any of the adversaries should not be able to inject any message to influence these parties. So this is a property to check the attack against the replay attack, and we need to also check about the non-injective synchronization. Synchronization is a property to check against the attack related to forward secrecy. We assume the Delavio threat model where we assume that the adversary has the capability to run multiple instances of the protocol, and it can trace back any of the old sent message, and it can resend the message to any other party. So while doing that, they should not be able to gain any of the information in the communication framework. So that needs to be properly tested by using the non-injective synchronization property, and this property is checked against the forward secrecy. So same properties need to be tested in the other side of the road. Say same secret of R1 R2 need to be checked. Px has to be alive throughout the session. Weak agreement, there should not be any message alteration or modification. There has to be proper commitment from both this side. Non-injective agreement and non-injective synchronization has to be properly tested. So this is the protocol that we have written. Now let us verify the protocol. To verify the protocol, we need to go to the menu verify. It's very simple, and you can click F1 as the function key to directly verify the protocol. Click here over here. There is some syntax error. Syntax error is simple. is some syntax error in the protocol. I guess, okay, I guess this is misplaced. This should be over here because we are using public key px to encrypt the whole message. So this is the whole message we want to encrypt. So this should be okay. Let us check. Verify the protocol. Verify the protocol. Yeah, I guess syntax is okay. It will take some time, probably 2 to 3 minutes. Yes, so we have the result here. So result is here. So we are seeing this blockchain, and most of the property that we are testing are finding okay. We are not having any attacks within the brown. So this is the comments or the result that we are having. No attack within the bound. It is verified over all the properties, and we looked at all the properties. I guess all the properties are working fine. Hence, the protocol is preserving the confidentiality of randomness R1, R2, message response and transaction are also confidential. The parties are alive throughout the system. There is no alteration or modification of message. The commitment or the trace is unique pattern. There is no non-executive agreement or disagreement. Their agreement over the non-executive message pattern. They're also following the non-executive synchronization property of Scyther and safe from forward secrecy kind of attacks. So this is all. Thank you for your attention.